Hello Beyond the Five students, my name is Angel Jimenez, and welcome to our last unit together. 7.9, Introduction to Le Chatelier's Principle, and 7.10, the Reaction Quotient in Le Chatelier's Principle. By the end of today's lecture, you should be able to identify the response of a system at equilibrium to an external stress using Le Chatelier's Principle, and explain the relationships between Q, K, and the direction in which a reversible reaction will proceed to reach equilibrium. Without further ado, let's get into today's last lecture together. So let's first start with, what is Le Chatelier's principle? Le Chatelier's principle describes the effects of an external stress on an equilibrium reaction. Oh, okay. What counts as an external stress? An external stress can come in three main forms: changes in concentration, pressure, or temperature. Now let's start with the changes in concentration. And so let's imagine you have an equation: A plus 2B is going into C. Now let's imagine you originally had 1 mole of each molecule at equilibrium. So you have 1 mole of A, 1 mole of B, and 1 mole of C. Now imagine we added another mole of the reactant A into the reaction. The reaction now has to deal with that new mole of A, and therefore it's going to use the rules of Le Chatelier's principle to deal with that stress. In this case, because the reaction was already at equilibrium when everything was at 1 mole, adding another mole places stress on the reaction that wasn't intended to occur. The reaction therefore needs to compensate for that extra mole in order to bring the reaction back to equilibrium, because now it's out of whack, and we're going to discuss why that happens specifically a bit later. So because the concentration of the reactants was increased, more products, or C in this case, will be made. And I just made an example that everything went down by 0.5. So you'll see that the 2 moles of A went down to 1.5 moles, the 2 moles of B, the 1 mole of B went down to 0.5 moles of B, and the 1 mole of C increased to 1.5 moles of C. And now the same would actually occur in the opposite direction if more products, or C, was added. So if we added another mole of C instead of A, then it would just, the same exact thing would occur just towards the reactant side. If more product is added to a reaction, then more reactants are produced in order to return the reaction to equilibrium. So why does this exactly happen? What's the specifics behind it? Well, it has everything to do with the reaction quotient Q, and it's very important that you understand why the change in concentration impacts the reaction so much involving Q. So Q is obviously a relationship, it's a comparison of the relationship between the concentration of the products and the concentration of the reactants. So when Q is equal to K, then the reaction is at equilibrium. So if we added more A, when we added that mole of A, we turn that relationship of products to reactants into the products being small and the reactants being big. And whenever you have a small numerator with a big denominator, your answer is going to be less than 1, or in this case, less than K. And K is going to be greater than Q. And if we remember from a couple of lessons ago, we remember that we were relating Q to K. And when Q is less than K, we are going to generate more products in a reaction in order to decrease the K value, in order to bring the reaction back to equilibrium, because when Q is equal to K, the reaction is at equilibrium. And so let's look at the exact same thing for the product side. If we added more C, or more products, then now the numerator, or the products, are way too big, and the denominator, which is the reactants, are small, meaning we're going to get a value that's greater than K, which is typically greater than 1. And now we have the same exact thing. We have a relationship. Q is now greater than K, which means that we are going to shift to the left side of the reaction, or we're going to make more reactants in order to lower that Q value back down into a level where it's equal with K and back at equilibrium. Now let's focus on the changes in pressure. This is the second external stress that can be applied to an equilibrium reaction. And so you'll see we have 2 liters of a very similar particulate model right here, and we can see that our K value, if we say that those molecules are in 0.5 m concentration, and we put them through the equilibrium constant, we're going to get a K value of 2, because 0.5 divided by 0.25, which is 0.5 times 0.5, is going to equal 2. Now, that was in 2 liters of volume. What if I cut that in half to 1 liter with the same exact molecules? Well, we need to figure out the number of moles of molecules we have in order to figure out what the Q is so we can compare the K to the Q. Then we know that when dealing with concentration, all we have to do is we have to take the number of liters we have and times it by the M, which is 0.5. So 0.5 times 2 is going to equal 1 mole of molecules. And 1 mole divided by 1 liter is going to equal 1 M. So now we're going to get a Q value of 1. And obviously 2 is greater than 1, which means K is greater than Q, or Q is less than K. And therefore, we're going to generate more products in order to balance the Q out with the K and allow for the reaction to return to equilibrium. So whenever the volume is decreased in a reaction, typically you're going to end up shifting the reaction to the right in order to produce more products to bring the reaction back to equilibrium. Okay, so let's do the same exact thing, except this time I've increased the volume to 4 liters. I went from 2 liters to 4 liters. So we're going to do the exact same thing. We're going to calculate the K value, which is still 2, the number of moles we need, which is still 1. Now we're going to calculate the new concentration at 4 liters, which is 1 divided by 4, or 0.25. When we put that into our Q, or reaction quotient equation, we're going to get an answer of 4. Now 4 is greater than 2. So therefore, Q is greater than K. And we know by that relationship that that means that we need to produce more reactants in order to balance that equation out and bring it back to equilibrium. So whenever you increase the volume, typically in a equilibrium reaction, by Le Chatelier's principle, you're going to produce more reactants in order to balance out the equilibrium. Now, there are some unique properties when dealing with gas volume changes, and these are very important to remember. Do not forget these, because they will determine whether you get a problem right or wrong. When dealing with a reaction with molecules in the gas phase, a decrease in volume will cause the reaction to focus on the side of the reaction with the less moles of gas. Now, that sounds weird and confusing, but just think about it. So if we have an equation, A plus 2B goes to C, and it's all in the gas phase, and we decrease the volume overall, we're going to look at how many moles are on each side of the reaction, the reactant side and the product side, because by that law right there, a decrease in volume, which we have, will cause the reaction to focus on the side with the lower amount of moles of gas. So we see that the reactant side has a total of 3 moles of gas, 1 from A and 2 from B, and our product side has only 1 mole of gas from C. Therefore, this reaction is going to shift to the right if the volume is decreased, because the product side has the lower amount of moles of gas. And it's quite true for the opposite. When increasing the volume, the reaction will shift to the side with the more moles of gas. So if we do the exact same equation, now, since we increase the volume, the reaction is going to shift to the reactant side, because that has more moles of gas than the product side. And now finally, the last thing about today's lecture is temperature changes and how temperature impacts an equilibrium reaction. So whenever you're changing the temperature of a reaction, you're also changing the equilibrium constant, which changes what direction the reaction shifts to, as we discussed before. So when you increase the temperature, you're typically shifting the reaction towards the left. And when you're decreasing the temperature, you're typically shifting the reaction towards the right. This is because you're changing the K value to reflect those changes. However, when you're dealing specifically with endothermic reactions, increasing the temperature is going to do the opposite effect. It's going to shift the reaction to the right with a higher K value. Decreasing that temperature will shift the reaction then to the left with a lower K value. And it's going to be the exact opposite for exothermic reactions. Increasing the temperature is going to lead to a left shift with a lower K value, and decreasing the temperature is going to lead to a right shift with a higher K value. It sounds confusing, but promise me, just work with it, and I know you're going to be able to get it eventually. Eventually, this is going to become like the back of your hand. You're going to know it and be able to understand it. And remember, this is all because of the relationship between Q and K, and how K works in equilibrium reactions, which we've gone over before. And that's it. That was my final lecture with you guys here at Beyond the Five. I'm so glad to have been given the opportunity to work with you. I know you guys are going to do great things in your AP Chemistry class or whatever classes you're going to be doing with. It's been a pleasure. Please do not hesitate to still reach out to me if you have any questions through Discord or through email. I will try to respond to you the best I can and as soon as possible. And for the final time, guys, I hope you found something useful out of this lecture, and I wish you all good luck with your studies. Goodbye.